Okay, so do you see my screen?
Yep.
Okay. Today we will explore fine-tuning process of Llama model, and it is a very big topic because we start large language models, and all the practice tasks in a lot of companies today. It is do something with large language models. Sometimes people use APIs, API, API to connect to these models, and we will look how can we do it in 1 week, like on the next lesson. But today we will go through how to fine-tune large language model. Today we will use not a large one, we will use a model with 1 billion parameters, but you can see that, let me show you, that you have on the Hugging Face a lot of language models with more than 1 billion parameter. For example, here is it. It is Qwen 2.5, and it is quite good today on all the benchmarks. It is a data set on which we can evaluate results of all the models. And it consists of a lot of exercises which large language models try to pass, and you can calculate metrics that you want to. So in this case, you will test your models, and as a result, there would be a leaderboard with results of all the models, and you can see how good is one model than other. And Qwen 2.5, it's quite good. This model is on the top of leaderboards. So, but we see that it is a very big size of this model. And today we will use Colab for fine-tune our language models. It was very important to me create Colab that you will be able to run by yourself. And because of this, I tried to use a lot of hacks which can help me to run these models on, let me see, here is, here we have T4 GPU. It means that we have only 16 gigabyte of memory on this card, and it's quite small. Usually nowadays, large language model engineers use A100 GPU or H100, and this kind of GPUs are about 80 gigabytes of memory. Because of this, we can say that 7 billion models will run on this GPUs without any issues. But if you will delete all the code blocks in this notebook, which attend some some functions to reduce parameters of the model, you will get the issue on training loop when you will run it. And it will be something that show you that you haven't got enough CUDA memory. So I will tell you right now how would we explore all these topics. Today we will have a large language model without any APIs. We will just train by ourselves model which we loaded from Hugging Face. On the next week, we will try to use it via API and API. And then on the third week, we will use, we will study for all the functions which we will we can use with large language models, and this yeah, and these technologies will help us to reduce parameters of the model, and we will spend 2 weeks on this. Then on the 5th week, we will study how to do okay, we name it RAG, R-A-G. It is technology with which we can show our model all the documents that we have, and it will answer based on this documentation. So I think it would be a lot of information for this kind of a month, a little bit more, but it would cover all the topics that we need to use on in real projects. So I think we can start from this point. And today I will explain you how to fine-tune Llama model. Llama is a state-of-the-art language model developed by Meta, designed to handle a wide range of natural language processing tasks, including text generation, question answering, and language understanding. We will have extra lesson on Friday, because for these topics, for this month, you will not receive recorded information with lectures by Radoslav. I will tell you by myself these 4 lectures, and I will do it on Fridays. So on next lecture, I will explain you why this kind of model can understand and can cover all the tasks on which in 2020s I mean in 2020 or in 2022 we used different types of models for all the tasks. I mean, if we wanted to do classification task, we used encoder only BERT, which we covered on the previous lesson. If we wanted auto-regression task, we used T5 for this. For example, we learned it when we covered translation task on our lessons. But now we can use one model for all the tasks. And in this seminar, we will guide through each stage of fine-tuning, covering both theoretical foundations and practical implementations. And by the end, you will understand how to fine-tune large language models and optimize them for specific tasks. But today, I will not deep to the details of optimize this large language models, because we will cover it in 2 weeks. But I will tell you all the information that you need to understand right now on this moment, in this moment. So here we setting up the environment in Google Colab, and we begin by selling essential libraries, for example, transformers from Hugging Face, which we used on previous lesson. Hugging Face library providing pre-trained models, tokenizers, trainer API for simplified fine-tuning, and I showed you 1 week before. Then we install Accelerate library to optimize memory and compute distributing computational across GPUs. It is library from Hugging Face 2. Here we can find documentation of this library. It's pretty easy. If you will try to use another backends for distribute training or for optimize your model, it would be much harder than use Accelerate. And usually on a lot of projects, NLP engineers, LLM engineers use this library, because it's like a constructor for a lot of backends, and you can use different techniques in one library. Then we, okay, there is one question. Collab configuration is not distributed. Yeah, it's true. We will not use distribute training on this seminar, because we have only one GPU for training here. But if you will use, for example, Kaggle, you will have 2 GPUs there. And in this case, you can use Accelerate library to distribute. And it's pretty hard topic. We'll not cover it on our lessons, but maybe if you are interested in this topic, I will show you essential documentations and maybe some papers, or I will send you information about different types of distribute training, but today no. But I noticed that we can do it with this library. Yeah. Yeah, okay, I will send different papers for cover these topics. Then we import bytes and bits. It's a library that enables memory efficient quantization, particularly useful for handling large language models like Llama. I will explain you what is quantization is, and I hope we will got all the information that we need to. Here I can check. What's wrong? Okay. I use this sense. So yeah, I can check the status of NVIDIA GPU, including memory usage and availability. Fine-tuning large language models like Llama requires substantial GPU resources, so it's essential to verify that your hardware meets the necessary requirements before processing. Here I explained you how we can see how much memory we have, and here we can modify how much memory we use. Also, if you will use not collab, maybe another environment, or I don't know, something that has terminal, you can also upload their NVIDIA, not NVIDIA SME, NVTop. It's I like use it, and you can install it with pip 3. So also you can install NVTop, but in this case you need to install this technique via Linux and from special repository. So I think it would be a little bit harder, but I like use not NVIDIA SME. I like use this two commands for monitor GPU status. Here we import libraries. We import necessary libraries for training pipeline. Here we can see auto model for casual LLM. I explained you on previous lesson how we can understand which class should we upload from transformers, and this class is suitable for task where output depends on previous tokens, such as text generation. Also, we import auto tokenizer, prepares text inputs by encoding them into tokens that the model can process. Also, we use here training and training arguments, simplify the fine-tuning process by handling the training loop evolution and parameter tuning. Then we use PyTorch library. We are familiar with this library, and logging to set up logging to track information about each operation, which is useful for debugging and ensuring smooth execution. So we setting up logging provides visibility into each step of the fine-tuning process, helping to monitor progress and catch up any issues that may arise. And in this part, I want to explain you a little bit deeper what is it Llama. Is a collection of foundation language models rating from in third generation it's ranging from 1 billion tokens to, oh my god, it's very big. Their biggest model, I think it's kind of hundreds of parameters. But in first generation, it was sizes only from 7 billions to 65 billions parameters. And it's trained on publicly available data sets. And you can use it on Hugging Face. I will show you how can you use it. So here I have access for the repository. But if you want use it, you need to. Okay, I will try to show you how to get access. Let's move to some collection in which I haven't got success. Okay. So when you not have access to their models, you go in through, here it is. So on this model card, you see that I haven't got access for use their models, and you need to fill in all the parameters of this form, and then tap submit, and they will receive you access to their cards and models. So I think you will do it, and then you will have access to their models. So let's continue. It's designed to achieve state-of-the-art large language understanding, while being computationally efficient. Llama uses a transformer architecture. It's not a vanilla transformer, it's a decoder-only transformer, and it's trained on trillions of tokens, demonstrated that it is possible to train state-of-the-art models using publicly available datasets exclusive without resorting to initiable datasets. And compared to the large language models, other large language models, Llama is notable for its open access approach, allowing researchers and developers to utilize and fine-tune the model for various applications. This openness fosters innovation and collaboration within the AI community. It's very nice because nowadays we have a lot of close models. For example, GPT-4 from OpenAI, Claude 3.5 from Anthropic, and it's very I like that we can attach some models, open models like Llama. So yes, here in this stage, we have a function that generates a synthetic dataset of arithmetic tasks for the model to learn simple calculations. By creating prompts that require the model to calculate sums or products of large numbers, we can train the model to handle numerical reasoning tasks. This simulated dataset serves as a foundational training set that we can use to access the model's capacity for basic reasoning. And here we build dataset, use dataset class to create training and testing datasets based on our synthetic arithmetic dataset. The training dataset consists of additional problems with numbers training from 2 to 18 digits, while the testing dataset contains the multiplication problems with number ranging from 2 to 10. This variation between training and testing task allows us to evaluate the model's ability to generalize beyond the specific operations on which it was trained. And let's see from which samples consist our dataset. I can run, I can print train data set, and how does it look like? You can see that it looks like dict, but and we can use it like a dict, but it's a class. So I want to see what is in the prompt of my data set, and I need to type the number of sequence that I want to get. So here I will see a string that consists calculate the sum of this number and this number, and I will get the result. And also I have a response key that consists value of the result. We need okay, we have it here because it will be useful when we will evaluate our model and see the result by ourselves. I mean that we will just print the result, and we will consist what print on the model and what we have. And here I ran this code block before the lesson, but we can run it here. I don't want to run it now because this means that okay, I use model for which I need get access. And if I will not do login command here, Hugging Face will not recognize that me as me, and I have access for this model. Because of this, they ask me for the token, and I will show you how can I get this token. So I can go to my user, sorry, it's access tokens. And here I can create a new token by create new token, and then I can copy it and I can use it. Of course, I did it. I did it, and I use my token for this notebook. Okay, let's move a little bit on, and here I will explain you. Okay, let's end with login. So it's this command just provide access to the Hugging Face model hub, and that's it. Here we configure bits and bytes for 4-bit quantization. And what is quantization? Quantization is a technique that reduces the precision of model bytes from higher 32 bits to lower 4-bit, like here, or for 8-bit. And do you have questions right now? Okay. So yes, and we here we provide quantization. Quantization reduces the precision model from 32 to 4 bits integers, cutting down the memory needed by the model. Here we imported bytes and bits config. It further optimizes quantization by supporting techniques like double quantization, which ensures accuracy by storing quantized bytes into smaller formats. Here we provide non-float for flag. This quantization type uses a memory-efficient data type for floating point numbers, improving speed without losing much accuracy. And also we provide BF16 or here we can't use BF. No, okay, it's all right. So yeah, we can. It's a 16-bit precision format that provides good balance of memory saving and computation efficiency. So you can search for this documentation and look through how does it look like and what we can pass here. Also, we can see a QLM config. It's a quantization by Yandex. It's very nice that we have here such classes in the documentation. So we can go to the source code, and then we can here deep in raw code and see how all the functions and classes communicate with each other, and how we get quantization. It would be a little bit difficult because transformer library transformer library okay, there are a lot of engineers who contribute to this library, and because of this, nowadays we have a lot of code blocks and code scripts. So sometimes it's very difficult to search for specific classes or functions. But it's nice that you have documentation, and here you can link to the source code block, and because of this you will not lose information that you need. So okay, let's run. Wait a bit. And okay, through these techniques, we reduce the memory load of Llama, allowing it to run on more affordable hardware while maintaining effectiveness. Here, we can load model and tokenizer. We load pre-trained model and tokenizer using specific configuration for efficient handling. Auto tokenizer prepares text inputs with start and end tokens was and the os added to structure the input. Also, we provided device map allow the model to be distributed across multiplies GPUs. But we haven't here multiplied GPUs, but we can pass it also. And quantization configurations we applied earlier reduce memory load, ensuring the model fits within hardware constraints without compressing performance. So here we passed quantization config, which we initialized before. And so what we have here, okay, and yeah, I added code line here to initialize part token. If we will import Llama model as this, we will not have part token there. And we can print what's now contains what our tokenizer consists. So you can see here vocabulary size of tokenizer for the Llama model. It's sentence piece tokenizer, and I can say in short information about this tokenizer. If we used on previous lessons tokenizers that used tokens per words and maybe other type of tokenizers, here our tokenizer consists of subwords, and how do we understand which subword should be only one token? Okay, how do we understand which subwords we need to initialize as a tokens? It's simply easy to understand. We can train our tokenizer, and while training, we will have big text. It consists of the words, and it's like a corpora on different languages, for example. While training, our tokenizer will understand with bytes operations how much one token appear with each other. I mean, how much subwords appear with each other, and will concatenate subwords which appears a lot with each other to one token. It's like a frequency of appearance all the symbols together. That's it. So and because of this, it's efficient, and we can use optimized counts of tokens for our models. Is it clear? If it is, and you don't have questions, yeah, let's move on. So yeah, here, and here you can see that we have some empty tokens in tokenizer. That means that you can add your OR tokens to the tokenizer, and usually people use it when they create multimodal structures. I mean, multimodal architectures with large language models. Okay, let's move on. So here we have tokenizing and our data set. Firstly, we tokenize, we convert text into numerical tokens that the model can process. We use map function to apply tokenization to each example in dataset, preparing the data for training, ensuring capability with model's input format. And you can see that I didn't provide context lengths of tokenization, and because here I don't want create batches, why is it why it is like this? Because I want okay. I want visualization of histogram of the distribution of token lengths across dataset, and it will help me determine the optimal max length for padding and truncation, understanding token length distribution, ensure the model process inputs efficiently, avoiding effective excessive padding that can slow down training. And here I identified optimal max length of my data, and here I provide it. So to the tokenize function, okay, I think maybe it would be interesting for you why I set result labels to result IDs. if we will understand what is going on here, we will see that that I tokenize prompt of my data set, and also I okay, if we will return to consistency of prompt in the data set, we'll see that here we have initial sequence which we want okay, we want to train our model to predict this last token. But it is auto-regression task, and on auto-regression task in the training loop, I train model to predict next token. So let's imagine that we have now word tokens to explain it a little bit easier. Here in the context, I have token calculate. I want to predict next token. And I will see on the context and count probabilities of next token. Then I will move on one step further, and I will have 2 tokens in the context. I want to predict third word, and then I will predict for this template as I explained to you. So, and in the auto-regression task, our labels would be our inputs IDs. On the each step, we will predict just a part of our sequence. Because of this, in auto-regression task, we just we set result labels as a result inputs IDs. So that's it. Okay, and here we have PEFT. We will learn it in 2 weeks, but I will try to explain you all the moments that you need to understand right now. So here I just use prepare model for K-bit training and gradient checkpoint and enable. That means that okay, what is, in a simple way, what is gradient checkpointing? On a forward pass, we calculate all the functions in our training loop. I mean, all the activations, we calculate all the matrices, and sometimes we have really difficult operations. Because of this, our backward pass would be a very hard process, and we want we don't want to spend our we don't want to spend our resources to calculate it for the second time, and gradient checkpointing enable us to calculate something on the forward pass, then set it to JSON or to some space, and then on the backward pass I will get it from the memory and just use it. That's it. And K-bit training is just we quantized our models and here we want to prepare it for the training. Also, how can we understand quantization? When we say that we cut okay, what do we say? That we cut our precision of the bytes, it means that in a simple way, from which parts consists our number. We have period and mantis. Maybe I name it in the wrong way, but I name it like on the Russian language. I'm not sure that it's right. So we can cut all these parts to get to reduce the precision, and all the types of quantization. It's to simple understand that we just cut different parts of our number. That's it. Okay, let's move on, and I will, in short, explain you what is PEFT and what is LoRa. We will learn it how I said before. Or I will run all the code blocks for training our models right now, because if I will not do it now, we will not get the result on the end of our lesson. Okay, it needs my 1B key. 1B, it's 1 second. It's a platform on which you can track. Yeah, thank you. On which you can track and monitor training loops of your projects. So it will log in me loss number or different values that I want to. It works like, okay, we saw it on previous lessons. We had clear-mail, we had what was on previous lessons. Yeah, a lot of yeah, thank you, MLflow. Yeah, exactly. So yes, and it's just another type of track progress of our model, but I like it, and it's very simple. It's okay. Maybe I will show you some graphics projects. For example, maybe this one. Okay, it was not a full training. Okay, we just maybe this one. Yeah, it's very beautiful graphics of different values of the training process. So okay, let's move on. And here we have LoRa approach. This is the function to calculate parameters of our model. It counts parameters with gradients enable, yeah, and all the parameters, and then it will print trainable parameters from the all parameters. So it's just a convent function to print how much parameters are not off in the training. And LoRa, it's a little bit hard to explain right now, because we will have lectures for these topics. But its approach is based on a key insight. In many large language models, most model bytes do not need to change districtly during fine-tuning to learn a new task. by identifying a small subset of crucial parameters and modifying only those, LoRa achieves nearly the same performance as full fine-tuning, but with far less computational cost. Here we provide target lawyers. We focus on lawyers like our attention lawyers, LM head, and adjusting these lawyers allows for substantial impact on model behavior without full fine-tune. Also, we provide low rank as a parameter, setting to the 32 reduces memory usage. Its a value would increase the model's adaptability, but require more memory. Also, we use LoRa dropout here. Dropout, we know that it's just a technique that will cut off our neurons on the training. It's edge regularization and scaling to prevent overfitting. More we will learn in 2 weeks. Here we define crucial parameters for training. We provided byte size to one to have if I would set batch size to bigger size, we will not be able to train our model on this GPU. Also, we passed gradient accumulation steps. It allows us to simulate a larger batch size by accumulating gradients over multiply steps, which improves training stability. And I passed learning rate, count of epochs, mixed precision training. Here, FP16. I can use on this type of GPU this type of precision. If I will have A100 or H100, I would be able to use BF16. Also, okay, we enabled login dictionaries or directories, I mean, and steps of evaluation. So here we have training loop and its class from hidden face. We can search for the documentation for this trainer. Also, we can deep in to the raw code and explore what the code blocks are they use for the training, but I will not do it right now, but you can do it at home. And it automatically handle data batching, gradient accumulation, logging, and evaluation based on the parameters we specified. These abstractions makes fine-tuning efficient, especially for large models like Llama. Then I do a train function that starts fine-tuning process, updating model parameters based on our dataset. I will stop right now training loop. There was 3 epochs right now, but we set it for 5. But I think we will be able to mention our results right now. So let's make evaluation. Once training is complete, we run evaluation function to measure model performance on the data set, on the test data set. This gives a snapshot of how well the model has generalized to new data and provides insight into any future fine-tuning needs. So here we can compare our training loss and validation loss. It's quite close, so it's okay. Here, this section tests fine-tuning model responses on specific prompts from this, what is going on. Okay, I just need to do something like this. Give me a second, just formatting. Okay. So here we comparing the expected and the actual outputs. We access the model's accuracy and its ability to apply learned patterns to arithmetic tasks. This also gives us an idea of how well the model has generalized from training data. So we can see that it's exactly the same, and we have exactly the same results. Here I wanted to provide inference of our model. Give me a second, because right now we will have the same result as we had on the previous step. So as you can see, 10 plus 15 would be 25. 4 plus 6 would be 10. And also we can provide another prompt for test task, and let's calculate multiplication of 2 and 8, and for example 9 and 5. Okay, 2 and 8 exactly the same, but as you can see, okay, sum, I didn't change, of course, I didn't change prompt. Yeah, it's exactly as we wanted. We made calculations from a large language model on this lesson, and this is final testing step. We input new prompts that the model hasn't seen before. So you can train large language models on tasks that you want to. For example, you can train on extract information from your data sets, and you just need to show it template. How do you want it to run, and then you will give if you will do exactly right steps on the training loop, you will get good result of using large language models. Do you have questions right now?
Yes, I had a question about the tokenization for big numbers.
Okay. And do you want explain me? Do you want me explain how tokenization is going on in sentence piece tokenizer for the
Yeah,
numbers?
I mean, maybe you covered this before, but so for our prompts involve like big numbers consisting of multiple digits. how tokenization work for big numbers?
It works exactly like on the text, but I think we will right now. I can show you how does it works. So here I had training data set. Okay, let's see how does it work on on response. I will create 1 second. I can see that here we have number, sequence of number, and I can show you how it would tokenize. Here we have 1, 2, 3, 4, 5, 6, 7 tokens. And
Yeah,
this
much more digits. So it's probably find the frequencies of digits that are coming together.
yeah, and also we can go to models card of llama. Llama 1 billion parameters. And there we would see in files, we will have tokenizer.json, or no, I need vocabulary of tokenizer. Yeah, I think maybe it would be okay. No, it is not a vocabulary. Yeah, here we have it. So let's search for this token. Okay, it's beginning of text. Yeah, exactly. Here, this is a beginning of text, and this is end of the text, I think. Let's start from searching this token. Here you can see when they trained tokenizer, 214 appears a lot of time, I think, and because of this, it created for the one token. Here we can see a lot of subwords, and you can see yeah, some different strange tokens. But on their text corpora, it was, I think it was a lot of times on which these tokens appeared. So yes, we can see that there are not only English tokens, but mostly they train Llama or English on English data. But also let's check. I think there need. I think that we can search for Russian words. Okay, no, I think I thought that we can search for Russian fragments of their text corpora, but no. But because they use no, sentence piece tokenizer, which work on bytes frequencies, if we will meet text on which we didn't see in text corpora on the training, it also can work on some new tokens, and also it can work on Russian language, but it would be not not good, not functional, and also it would be much better if we will add Russian tokens to tokenizer. Firstly, we will train Russian tokenizer, and then we will add it to the model. Then we will just resize embedding size of the model, and that's it. I think that's all. Okay. So if you don't have questions for today, it was, I think we covered all the information, and it was maybe pretty difficult, I don't know, but thank you for your attention.